Okay, 1, 2, yep, right. Okay, I think this is the correct mathematical model for the double slit experiment. All the maths is correct. It gives all the right answers for the intensities and the angles. So why hasn't it been discovered? These are the two base units. L is the Lorentz transform, and then the big blunder of Einstein was to use gamma, which is 1 over L for time, instead of realizing that he had velocity, v over c, which is b, and he had distance, which is L. He could have just gone b is equal to distance over time, which is L over capital T, and then you rearrange that and you got your capital T. So that's time. And although if you've got two frames of reference, you do use gamma to transform between capital T and T over L. T is the key, because T is the function here, and it's orthogonal to space. So I've got the relativistic slide rule, which is the fermion, and there's one slit and there's the other slit, and it goes and the actual particle, according to the interpretation I'm going to use to start with anyway, is the de Broglie one, and that is that it slit goes through, the particle only goes through one slit. So there's particle A going through one slit, and as to how it's guided across to the probability wave, there's 3 possible interpretations for that, and I haven't just decided on one, but I'll just note all 3 of them. So first of all, noting that the distance between the slits is always equal to 2 times t. So the distance from there, 0 to there, is t, and so 2t is actually the distance between the slits. And in every case, A, which is the slit width divided by the wavelength, always equals 2 in this model. So that's the distance between there and there is 2. Okay, so I'm postulating that a particle goes through one slit, and then either travelling along this t function, which I call a line of simultaneous time and space circumference, because it is a line of simultaneity, I believe. Then you'll find that this A, sorry, this is the line of simultaneity here, t. The diameter is t, and you find that the particle is always on that circumference. There's its initial position, and its final position is also on the circumference, and this is always the case. Okay, so that's why I'm suspicious that that might be the path that it takes once it's gone through the slit. However, there are other interpretations, because there is also this trajectory, which is arises from the phase wave interfering with itself. And there's also a third possibility, which is this one here, which is the travelling, I'm saying backwards in time, because the clock has moved forwards from being up here to there, in time down to the black 1 over b impedance line, which is that one, to the centre here, and then from there it heads out along a probability wave trajectory. So I got those 3 possibilities. But anyway, just get rid of the RSR and the t function, And just to prove that they are in fact following those trajectories, you can see that the orange one is actually following the phase wave interference trajectory, and the black one is actually following the probability wave interference trajectory. Okay, so and that's true in all cases. So for example, if I well, no, I'm not going to go into that. You'll see that it's true. Okay, now I'm just making V any old value, but I do like the natural log of 2, because then I find that the angle when M is 1 is seems to be exactly the Weinberg angle. Okay, so I have to investigate that more to make sure that I get exactly the right mass for the W boson, but I know already that that is about what I get. Okay, now I'll just play with these, the B value and the. So let's play with it a bit. So here's the. Better put my RSR in anyway. Put the T function in too. So you can see here the distance is decreasing between the slits, and the diffraction is increasing now, and then heading the other way as the distance increases between the slits, the the diffraction decreases. You're getting more and more fringes. See there, the number of if I increase that, the number of fringes is increasing, and you'll notice that the I'm just going to quantize that, make it 1. You'll notice that the intensity is roughly the same but decreasing slightly. And how did I come up with this these intensities? Well, I had to combine the ideal double slit interference, which is that purple one there. I had to combine that one with a one slit envelope, which is that one, that blue one there. And if you combine them, and the way to combine them, I discovered by experiment, is actually to multiply them together, not add them, and then square it, and that gives you that red one. So let's just change the B value here. You can see it all works out. Okay, so that all looks a bit messy. The only thing you ever see is that pattern on the screen, that red pattern there on the screen. That's the only thing you see. And you know, if I don't quantize M, then you get this intensity just going up and down with the fringes, and that's the correct value for the intensity. It's a ratio of the intensity to the initial intensity. These are the correct values. And notice they're perfectly sitting on, here M is 4, perfectly sitting on, but if I start to increase B, it starts to go a little bit. It's all good to about 0.3 and 4, it's all good. Just bring that down to 1, and which is the examples they always use in the textbook. But as you notice, it's starting to get a bit off. As your my T is getting higher and higher. Now it's a little bit off. Now if I go to my favourite B value, which is 0.6, see it's slightly off now. So what's actually happening is you can see that it's actually approaching T itself, and T is actually the first minima of the wave envelope. So I've put that back in the blue one. See how it's right on there? And that's because the slits are getting closer together, so you're basically starting to talk about just one slit. So in fact you can just make M equal to 1T, and you're spot on there. And now it'll always be the first minima of a single slit, because that's where T is. See how it's just moves with it, and the angle doesn't change, and this angle is 30 degrees. That's probably all I need to say for now. Oh, I can prove it with an example. This is the example they have in the textbook here. So let me just match it up by getting the T value that they've used, which is the square root of 1 divided by 1 plus, and now the T value they've used is a distance between the slits of 0.35 millimeters, and the width of the actual slits themselves is 0.055 millimeters, and it's a ratio, so I can leave it in millimeters, and then square that and you get the B value. And notice that it's spot on. So let me just notice my I'm on the first minima because I've made M equal to T, but if I make M equal to 1, notice that now it's just spot on the first fringe, M1, M equals 1. And now I can go to M equals 2. There you go, I'm right on top of the second fringe. I can go to M equals 3. And now I'm right on top of the third fringe, right on top of the fourth fringe, and the fifth fringe. And notice that as long as M is less than T, you're pretty much in the way, you're pretty much seeing the fringes. But as soon as it's equal to a T, you're at the first minima, so the fringes are gone. So anyway, that's one proof. That's enough for now, I think.